Welcome back. Let's talk about something called the common ion effect. The common ion effect addresses the question of what impact on solubility does having another chemical in that same solution have. So for example, if I have some solid silver chloride and I put that into a solution of silver nitrate, is the solubility of the silver chloride going to be increased, decreased, or is it not going to be affected at all? To address this question, we are going to start with the solubility equation. So we're going to write a dissolution equation for silver chloride, and we're going to write the KSP expression that corresponds to it because this is an equilibrium process. And then we're going to apply logic. So if I have a solution that has silver nitrate in it as well, when I go to drop the silver chloride in, there's not going to be a chemical reaction because I've got the same ions and then nitrate, which we know is a spectator ion. So if I don't have a chemical reaction, I can impact this equilibrium. We know that the KSP value, which we're told here is 1.6 times 10 to the negative 10th, is the equilibrium amount of the ions that we can have in solution. So if we already have silver ions in solution, then it'll take less of the silver chloride dissolving before the concentration of those ions are large enough that we're at equilibrium. Because there is already some of those ions in solution, less of the solid will dissolve. And that is the common ion effect. This is only impacted by ions that are found in that solubility constant expression. If something like nitrate, it doesn't matter what its concentration is. It doesn't impact KSP. It doesn't impact your value for Q. It doesn't change where your equilibrium lies. But one of the ions that is in that equilibrium constant expression will have an impact. And so we say that a common ion is going to decrease the solubility of a solid. Well, how much? Let's take a look and actually do the math. So same problem, my silver chloride is being dropped into 6.5 times 10 to the negative third solution of silver nitrate. We already know it's going to be decreased, but now I want to number it in order to compare it. So we're not doing anything different. We're going to take all the equilibrium tools we've been using and apply them here. So we're going to start by writing a balanced chemical equation, the KSP expression, and setting up an ice table. So here's where we need to be aware that we're doing a slightly different type of problem. So I know that the amount of solid I have isn't going to impact my equilibrium constant expression. I know that I don't have any chloride ions to start with, but now because of the silver nitrate, my initial concentration for the silver is 6.5 times 10 to the negative third. Then a small amount of the silver chloride is going to dissolve, so we'll have a little bit of that dissolve. And therefore at equilibrium, I know the concentrations that I have. And for the silver ion, that's the initial starting concentration of silver plus the little bit of additional silver that was formed by the dissociation process. These can get plugged into the KSP equation. At this point, if I want to solve this, I would need the quadratic formula, but there's a trick. So we already know that only a little bit of the silver chloride is going to dissociate because KSP is 1.6 times 10 to the negative 10th. And I know that because there's silver in solution, even less than usual would dissociate. So the amount of additional silver that's going to be formed compared to the amount of silver that was there in the beginning is going to be negligible. And so we can say that 1.6 times 10 to the negative 10th is going to be approximately equal to just 6.5 times 10 to the negative third times x. You can only ignore the change in concentration where it's being added to a larger amount. If it's being multiplied, that has a huge impact, large or small. But addition, if you have 6.5 times 10 to the negative third and you add, just for numbers' sake, something times 10 to the negative sixth, it's such a tiny addition you don't notice the difference. And so we're going to allow that term, the x, to be considered negligible in that addition term. And then once you've done that, this becomes very easy to solve. And so at this point, we can see that the molar solubility for silver chloride would be 2.5 times 10 to the negative 8th moles per liter. If we wanted to know about that in terms of solubility, so in terms of grams, we can use the molar mass of the silver chloride. And we see that the solubility of the silver chloride would be 3.6 times 10 to the negative 6 grams per liter. So that's a tiny number. But how does it compare to what it was before? In pure water, this same solubility is 1.9 times 10 to the negative 3rd grams per liter. So we're about 1,000 times less soluble in this silver nitrate solution than it would be in pure water. So again, if you're adding a common ion to the solution, so an ion that's in your KSP expression, you're going to decrease the solubility of the solid, and generally you'll decrease it quite substantially.